This lesson is about logarithms as inverses. You may not have heard this word logarithm before, but you've probably seen the log button on your calculator, L-O-G. That's what we're going to be talking about today, and we're going to see how that works as an inverse and what it's the inverse of. So the first part of our note says a logarithmic function is the inverse of the exponential function. Its graph will be a reflection over the line y equals x. So we saw that in our notes from last lesson where we have y equals x, this line right here with a slope of 1 and a y-intercept of 0, that we can find an inverse for any function of by reflecting over that line. So the first thing we're going to do is find some values for y equals 2 to the x power. You can use any values you'd like to for x and then see what you get for y. Usually when you're evaluating equations, it's best to have negative and positive values in your table, and also a 0, because things happen at 0 that don't happen anywhere else. That's also our y-intercept, which is an important feature of any graph. So if I substitute negative 2 into the equation, I have y equals 2 raised to the negative second power. Now remember, when we raise things to negative exponents, we can rewrite that as that whole power, 2 to the negative 2. We flip it to the denominator, and now it has a positive exponent. And 1 over 2 squared is the same thing as 1 over 4. So when we evaluate the function at negative 2, we get 1/4. Now let's try at negative 1. This is y equals 2 raised to the negative first power. That's equal to 1 over 2 to the first power, which is equal to 1 over 2. So 1/2. The third one, 0, I'm going to erase this to make some more space. If I evaluate the function at 0, y equals 2 raised to the 0 power. This one people miss a lot. They say that it's equal to 0, but anything raised to the 0th power is always going to be 1. Now for the easy ones. If I do y equals 2 to the first power, 2 to the first power is just a 2. And y equals 2 to the second power, or 2 squared, and that's a 4. So those are easier to evaluate because we've done them many, many, many times before. Now let's graph these ordered pairs. Negative 2, 1/4. That's over negative 2 to the left and up 1/4. That's really hard to graph precisely. Now for negative 1 and 1/2. If we go over negative 1 and up 1/2, we're just a tiny bit higher than the last one. Over to 0 and up 1, just a tiny bit higher than the last one. Over to 1 and up 2. And then over to 2 and up 4. Now we could do some more. If we do 3, we would get over to 3 and up 8, because 2 cubed is 8. So now you may remember seeing this function graphed before. Exponential functions get really big really fast. So you can see how this function looks when you graph it. Now we want to talk about its inverse. The inverse of this, remember from yesterday's lesson, is what we get when we reverse the x's and the y's. So I'm going to have 1/4 paired with negative 2. I have negative or positive 1/2 paired with negative 1. I have positive 1 paired with 0, and positive 2 paired with 1, and positive 4 paired with 2. So what we're going to do is graph these ordered pairs and see that they are indeed a reflection over the line y equals x. So when I graph 1/4 negative 2, I'm going to be right about here. When I graph 1/2 negative 1, I'm going to be just a little bit above that. When I graph 1, 0, just a little bit above that. Then 2, 1 is about there, and 4, 2, a little bit over from there. We also graphed 3, 8, so let's graph 8, 3, which is about here. And now I can draw in this graph. So you can see that we do have a reflection across the line y equals x. Notice how in the exponential graph that we graphed with this table, we had what's called a horizontal asymptote at the x-axis. When we graphed its inverse using this table, we had a vertical asymptote, and the asymptotes will never be touched or crossed. So keep that in mind when you're drawing in your graphs, because sometimes people like to cross those lines and we're not supposed to. All right, so what about domain and range? Now, we just talked about those asymptotes and the fact that we can't cross them or touch them. So while I can substitute any value in for x in my exponential equation, I can't do that for y. So the domain for the exponential equation is going to be negative infinity to positive infinity, because this graph will never stop going left or right. My range, though, it's not going to go up and down forever. It goes up forever, so the upper bound would be positive infinity, but it stops going down at 0, and in fact it never really touches 0. So we have the parentheses there. Now in the other one, the logarithmic function graph, the domain is the one that's restricted. So for the domain, we can't go left and right forever. In fact, we start at 0 without touching 0 and go to positive infinity. For the range, though, this graph will never stop going up and down. So the range is negative to positive infinity. All right, so what ends up happening, as you've seen in our two equations that we started with, is that the function y equals log base b, we call this little b a base, so y equals log base b of x. I'm going to write that out so you know how to read it when you see it again. Notice that a logarithm is equal to an exponent. So whatever we have over here on this side of the equal sign in a log equation is going to be an exponent previously. And that's hard to tell from what we just did, but you'll see it happening in the next examples we do. In these problems, the base can never be less than 0. It has to be greater than 0, so positive numbers only. And it also cannot be equal to 1. So greater than 0, but not equal to 1. So here's the rule that we're looking at. We've got if y equals b raised to the x power, that's an exponential equation, and here's my exponent. In the logarithm, the log is going to be equal to the exponent. So keep that in mind. Logs are always equal to exponents. Also notice that the base of the exponent, the b here, is the base of the logarithm, the b there. And then the y fills in the empty spots. The easiest way that I've ever seen to work with these problems is using a loop or a log roll. So what you're going to do to change from exponential to logarithmic or from logarithmic to exponential is start at your base, which is b here, go around the equal sign, and land next to where you started. So you start at the base. Your base is going to be the same in both of them. You go around the equal sign. The next thing that you see is the y, so that's the next thing you write when you do your log, and then you land back where you started. The last thing you see will be your exponent. So if you use the log roll, you'll be able to change from an exponential to a logarithmic. So I'm going to write down those instructions so that you know how to do this in the future. So when we do the log roll, we begin at the base, we go around the equals, and we stop next to where we started. So let's see how that works in these first problems where it says to write the exponential expression as a log. We're going to begin at our base, which is 9, go around the equal sign, and land next to where we started. Now we had an exponential. which means our inverse is going to be a log. So I'm going to write the word log. I'm going to write the base, 9, little and down a little bit lower than the word log. The next thing that I got to when I was doing my log roll was an 81. And the last thing I got to goes on the other side of the equals. The exponent is what logs are equal to. So log base 9 of 81 equals 2. In the next one, begin at your base, go around your equals, stop next to where you started. So I'm going to have a log. This time the base is 7. The next thing I saw was a 1/7, and the exponent is -1. Logs always equal the exponents. In the next one, begin at the base, around the equal sign, back to where we started. Log base 2 of 32 equals the exponent 5. And finally, begin at your base, go around your equals, land next to where you started. Log base 3 of 27 equals x. So your base matches your base in both of them, and your log equals your exponent in all of them. So filling in these blanks now, it says the base of the exponent is always the base of the log. So those two are going to match. And the exponent is what the log is equal to. So those are two things that we've already talked about. We're just putting them in the blanks so we remember them for later. Now, we're going to do the reverse. We're going to write the log as an exponential expression. If you have a log to begin with, you will not have a log in your answer. We're changing the logs to exponentials. So we still start at the base, we go around the equal sign, and we land next to where we started. So the base 3 is still the base in the exponent. The next thing I got to with my log roll is the x, and the exponent is what the log is equal to. So 3 to the x is equal to 8. And the next one, start at your base of 5, go around the equals, and land at the 25. 5 raised to the second power equals 25. We started at 5, we went around the 2, and we landed at 25. Next, start at the 2, go around the 7, land at the 28. 2 to the 7th equals 128. And finally, start at the 6, go around the 36, and land at the x. 6 to the x power equals 36. So the base of the log is always the base of the exponent. And the log, what the log equals is the exponent. So summarizing everything we've talked about so far. Now, it says evaluating logarithms. So we want to find the correct exponent for the base of the log. So here, we have a logarithm, but we don't have an equal sign like we saw in all the other problems. One thing that I like to do on these is to put an equal sign. I don't know what this is equal to, and that's what I'm trying to find out. So I'm going to put equals x. It could be any letter you want it to be. You could even put a question mark if you want to. The whole point is we're trying to figure out what these are equal to, and we don't know what they are. So we're going to use our inverse log roll to help us find out what they are. So again, we're going to start at the base, go around the equals, and land next to where we started. So 13 raised to the x power equals 169. So the question you have to ask yourself is, what exponent could I replace x with so that 13 raised to that power is equal to 169? And the answer to that question is 13 squared is 169. So x has to equal 2, which means the answer to this logarithm is 2. Or I can just write the 2. I don't have to write the x equals, because remember, I added that x equals in there. So we can remove that and just say this is equal to 2. For the next one, we're going to do 2 raised to the d power equals 1024. So what exponent could I put on the 2 if I start at the base, go around the d, and land at the 1024? 2 to what power equals 1024, 1024? Now, I didn't know this one to start with, so I had to use my calculator and see how many times I could multiply 2 times itself to get 1024. And it turns out that I have to multiply 2 times itself 10 times. 6, 7, 8, 9, 10 to equal 1024. So my d value is going to be 10. And that's the answer when I evaluate this logarithm. In the next one, 4 raised to some power, I used a question mark for this one, equals 64. How many times do we multiply 4 times itself to get 64? 2 gives us 16, but 3 for the exponent, 4 to the 3rd power gives me 64. 3 to what power? And I used a y this time. 3 to what power equals 81? Well, 3 to the 1st power is 3. 3 to the 2nd power is 9. 3 to the 3rd power is 27. 3 to the 4th power is 81. So my exponent is 4. What exponent do I need for 5 raised to that exponent is 625? Well, 5 to the 1st power is 5. 5 squared is 25. 5 cubed is 125. 5 to the 4th power is 625. So my exponent for this one is 4. 5 to the 4th power is 625. And finally, what power can I put on a 7 so that I get 343? So 7 to the 1st power is 7. 7 squared is 49. 7 cubed is 343. So my exponent is 3 for this one as well. Now, the last thing we need to discuss before you try some problems are common logs. In common logs, which is what your calculator has a button for, the LOG button is for your common log. In common logs, the base is 10, but it's understood, meaning that it's not written there. So we have to know that it's a base 10 even though we don't see it. So that means that in this first example down here, I've got an understood base 10 right here. So that's log base 10 of x equals 2. And I've got to find out what x is. So I'm going to do my log rule, 10 for the base, 2 for the exponent, equals x. Well, 10 squared is 100. So x is equal to 100. Now what about the one right below it? In this one, we are doing log with an understood base of 10 of x equals 4. So 10 to the 4th power using my log rule equals x. 10 to the 4th power equals x. Well, 10 to the 4th power, if you do that in your calculator, or if you just remember that when you put exponents on a 10, the exponent on the 10 gives you the number of zeros that you have. So here my exponent was 4, I have 4 zeros, and the last one my exponent was 2, and I have 2 zeros. We can use that to our advantage as well. In this one over here, we still have a base of 10, and this time we're asking ourselves, what exponent do I get? 10 to what exponent gives me 100? 10 to what exponent gives me 100? Well, 100 has 2 zeros on the end of it. So the exponent I need is 2. In the next one, 10 to what exponent gives me 1,000? 10 to what exponent gives me 1,000? 1,000 has 3 zeros on it, so the exponent I need is 3. And finally, we have 2 final examples. Log base 10 of 10 equals what exponent? Well, 10 to that exponent will have to equal 10, and this has 1 zero on it, so we're going to have a 1 for our answer. And the last one we have here, says 10 raised to what exponent, we'll use an x for that, equals 1. 10 raised to what exponent equals 1? Well, 1 has no zeros on it, so we get 0 for our exponent. Remember, anything to the 0 power is just 1. Now, what would happen if we had log of base 10 of 0.01 equals x? What would x be then? Well, here our understood base is still 10, so I've got 10 raised to what exponent equals 0.01. I can't just count the zeros here, because even though I see 1 0, that's not how this problem works. For this one, my answer is going to be -2, because I have to move this decimal place 2 places to the right in order to get a 1 again. So my exponent is -2. You can try that in your calculator. 10 raised to the -2nd power gives you 1 over 100, or 0.01. So look out for those in the future. Try the rest of the problems and see if you can get those.